Okay, Bismillahirrahmanirrahim. Assalamualaikum and good morning. Okay, so today this is actually you are watching a recorded lecture for lecture 9. For the rest of the subchapters that we have not covered from on last Monday. So as we can see from this planning, for chapter 6, we have only completed pressure control valve application and also B, automatic cylinder reciprocating system. And today I'm going to deliver a lecture regarding the regenerative circuits, lock cylinder using pilot check valve, synchronizing circuits, and also metering in versus metering out. So last time we stopped until here. So let me check whether this is already recorded. Okay, good. Okay. Okay, so this is a basic diagram for a regenerative cylinder circuit. So why do we call this as, why do you see the term regenerative? Because you can see the main difference from this regenerative circuit compared to the conventional one is that the outlet line coming from the cylinder here normally is being fed or is being channeled to the tank. That is for the conventional one. But for the regenerative type, you can see that the let's say this is hydraulic. So the oil coming out or leaving from the oil leaving from the cylinder will now be fed back to the supply part of the DCV, and therefore it will be used again together with the oil coming from the pump itself. Okay, so the purpose of having this regenerative circuit is to speed up the extending speed of the double acting cylinder. Okay, so you can see that with this kind of configuration, the speed that is going to be faster is only during the extension, because you can see that during the extension, the flow coming from the rod end regenerates. So this is the rod end. Okay, the flow coming from the rod end will regenerate with the flow from the pump. So we have two, from the rod end and also from the pump. So it will provide a greater flow rate. Therefore, the operation of the cylinder during the retraction is still the same, except for wait 1 second, I have call. Hello, salam. Yeah. Okay, sorry for the interruption. Okay, so you can see that by having this. Oh, yeah. Hello. Yep. Okay, sorry for the interruption again. Actually, we have for those who are in Malacca, you know that last Monday or Tuesday, there are few places got affected by the flood. Okay, so I'm one of the committee in charge for the to collect and to deliver the donation from our staff in order to deliver to the victims of the flood. So tomorrow we have to go out and deliver to those houses affected. That's why I need to call this. Okay, so you can see the retraction is the same, but only the speed during extension is actually being increased. Okay, so it's the same. During the retraction is the same as the regular double acting cylinder. Okay. So this is when we want to look into the calculation. All right. So the flow from the pump is denoted as QP, and the flow rate from the pump is denoted by QP. The flow rate from the rod end or the written one QR is denoted by QR, and therefore you can see that the flow going into the blank end of the cylinder. Okay, this is a blank end. This is rod end. I hope this one you should be already familiar with this term. Okay, so the flow coming through the black end is now equal to QP plus QR. So QP equal to QT equal to QP plus QR. And then if we solve for the pump flow rate, QP then equal to QT minus QR. Okay, QP pump flow rate is QP, right? And then we know that from the previous lecture, you know that the formula for velocity is actually equal to Q divided by area, right? So here we get Q actually equal to velocity times area. So for the total flow rate, which is here, the effective area is AP. Therefore, for the total flow rate, it is equal to AP times the extent velocity, because we are talking about the extension now. This one, extension. And then QR is actually equal to the velocity, the same velocity, V extension, but now the effective area is actually AP minus AR, which is this, what do you call this? The ring area, okay? So when you rearrange this formula, you will get finally V extension for the regenerative cylinder circuit is equal QP divided by AR. Okay, so bear in mind that this is very different from the normal circuit. For the normal circuit before this, if you remember, the flow rate is QP divided by AP, right? But now, if you have a regenerative circuit, this formula is no longer correct, because now you have to use this formula to calculate the extension velocity for the regenerative cylinder. However, for the retracting speed, the formula is the same with the previous or with the conventional circuit, which is QP divided by AP minus AR. And that is why it says before, the retraction speed is the same as the regular double acting cylinder, and it is also proven from this formula as well. So when we want to find the ratio of the extending and retracting speed, which is V extend divided by V retract. So if we rearrange the formula, we know that V extend is QP over AR and V retract is QP over AP minus AR. So you insert those into this, and then finally you get the ratio between extend and retract speed is AP over AR minus 1. Okay. And then in terms of the force or the load carrying capacity during extension, we can calculate by using the formula of P times AR. Okay, so take note that this is again also different from the conventional one, where for the load during extension, you multiply with AP, the piston area. But for the regenerative circuit, you have to multiply pressure with the rod area. And from here, we know that AR is always less than AP, right? You can clearly see from the diagram. AP is the whole area and rod is only this one, right? This one, AR. So we can say that the force during extension for regenerative circuit is less than the one using the regular double acting cylinder without any regenerative line like this. Okay. So this is because the system pressure. During extension for regenerative circuit, the pressure acts on both sides of the piston during the extending stroke of the regenerative cylinder. So you can see during extension, the pump will still supply the flow. So there will be also pressure being acting on this side as well. Okay, because this line is open. Okay, and also of course we have this line, which is directly from the pump. So when you have both pressure acting at the same time oppositely, therefore it is very logical that the force during extension in this case is less than the conventional one, where you only have supply going through the blank end but no supply during through the rod end. But for regenerative, you have both through the blank end and also through the rod end, and they act oppositely. And meanwhile, for the during the retraction is still the same with the conventional formula, where the pressure time the force during the retraction is equal to force times AP minus AR. Okay, so that's about the regenerative cylinder circuit and how it differs from the conventional circuit without any regenerative line from the rod end back to the supply and to the blank end of the cylinder again. And now we want to look at how can we lock the cylinder with pilot check valve. Okay, so in many cylinder application, sometimes it is necessary, okay, for a certain application that you need to lock the cylinder so that the piston cannot move due to any external force acting on the piston rod. So you want to keep the cylinder static or lock. So in order to do this, you can use pilot open check valve. This is check valve. This is the symbol for check valve. We have two here. But the difference is this is a pilot open check valve. Means for a normal check valve, you know that for a normal check valve, it will only allow the flow. In this case, it will allow the flow in this direction, right? You have the flow. Okay, and then it will block in this direction. So this is a normal check valve. But when you have pilot open check valve, this is a special feature of a check valve where, in this case, you can also allow the flow in this direction because you have the pilot line, and the pilot line will help to push this ball a bit to the side, and then the flow can go through. Okay, I hope you can imagine. Okay, that is the difference between the normal check valve and the pilot open check valve. For pilot open, you can also allow the flow in the opposite direction by having the pilot line. You can see this dashed line here is a pilot. Pilot means you have a flow of oil which will be supplied to push the ball. In this case, it can push the ball a bit upward. So there will be some opening down here, and then the flow can go through in this direction. Okay, so you can do the locking, cylinder locking by using pilot open check valve. Okay, by which the cylinder can be extended and retracted as normally done by the action of DCV. So if the regular check valve were used, the cylinder could not be extended or retracted by the action of DCV. So if you use only the normal check valve like this, without the pilot, then the cylinder cannot be extended or retracted by the DCV. Let's see. Okay, let's try to simulate. Okay, let's say you have two positions. As usual, you have position A. This is position neutral or 0. Damn it. F0, alamak. You have B here. Why when I want to draw 0 is always this problem? Never mind, I will just keep the 0. So you have position A and position B. So in order to extend the cylinder, you have to activate position A. So when you activate position A, let's say this is port A, this is port B lah. Ini pun sama, this is port A and this is port B. Ayo. Sensitive with any curve. Oh, okay. Never mind lah. So you know that there is port A and port B. Okay, this is port B. Okay, in order to extend the cylinder, port A will be position A will be active, and port A will be connected to here. So this is port A. So this is port A, this is port B. So when it's connected to port A, and then you can have this flow through here, right? Flow. Maybe I can just use pointer now. Sorry for that. Okay, so you have flow through A. And then this is a free flow because the check valve is in this orientation, so you can flow through. You can flow through this because the ball is upper and this the ball is up and the seat is down. I mean, like with this orientation, you can have a free flow. So and then cylinder will extend. When cylinder extend, the oil will leave through this rod end. And now, if there is no pilot check valve, there is no way that you can extend this piston because the flow here is stuck. Because in order for you to move the cylinder to this direction, the flow must go in and the flow here must also leave. Therefore, you have a space here, right? So that the piston can extend. But now, since we use a pilot open check valve, what happened during this time? The pilot check valve will push the ball upward, and then the flow can go through the check valve, and then it will go back to the tank through position A through port B here. So B to tank. Okay. And then to retract the cylinder, you have to activate position B. Okay. To activate position B, now you can have the flow going through port B, and through port B, then it should be here lah. Port B, and cylinder will retract, and then the pilot line will open the check valve, and the check valve will allow the flow to the tank from A to T. Okay. So the purpose of having this is that you can see that even though that the purpose of this circuit is actually to lock the check valve, but we also want to make sure that we can also extend and retract the cylinder when it is necessary. Okay, so just imagine if you use the same configuration of the DCV, but you only use the normal check valve. Yes, you can lock. Okay, you can lock your cylinder, but when there is a need to extend and retract, that cannot be happen because the check valve will block the flow during extension and also during retraction. Therefore, this is important to use pilot open check valve together with this 4-3 DCV with this neutral position. So this is how you can perform cylinder lock. Cylinder lock is in this neutral position. So you can see that there is no flow coming, it's being blocked, and therefore nothing will happen to the cylinder because there is no oil movement in this area because of the blockage in this position. Okay, and then we want to look at how can we synchronize circuit when we have more than one cylinder. In this case, we have two cylinders connected in parallel. So, okay, this is in parallel. So you can see this is how it's connected in parallel. So ideally, okay, even though you can see that the cylinder looks the same from the figure, but ideally they are not exactly identical. Okay, because the cylinder with the smaller load, let's say this two cylinder is not exactly identical. So what happened? The cylinder with the smaller load will extend first because it will move at the lower pressure. So when you have a cylinder with smaller load, means it only needs a lower pressure. So this one will extend first. Okay. So after this cylinder has fully completed its stroke, then the system pressure will increase. So for example, this is smaller. Okay, this is small. So this is a smaller load and this is higher load. Okay. So in this case, this one will extend first. So once it's already reaching the maximum position, okay, the piston is here. Then what happened? The cylinder, the pressure will start to increase lah because there is no more, there is no way that this piston can move any further. So what happened? The pressure will increase, and when the pressure increase to the higher level, then the cylinder will with the higher load will then extend. Okay. So in this case, we cannot synchronize the circuit unless we have both cylinder have exactly identical feature. Means that exactly same diameter, exactly same stroke, and exactly same size. Then you can have cylinder to move in synchronous. Otherwise, the smaller load will extend first, and then the bigger one will extend after the first one is finished, has finished extending. So as I mentioned just now, in reality, there's no two cylinders are really identical. There should be a very small difference, okay? Because of the difference can be due to the friction, and this will prevent the cylinder synchronization. So in order for us to make sure that we have a fully synchronized, you have to make sure that the friction effect is also the same between the two cylinders. So let's see this example.
This shows a synchronous circuit with two cylinders connected in series, with two position indicating limit switches and a replenishing valve. Circuits like this require a replenishing circuit to replace leakage oil. Both cylinders have the same area where their ports interconnect. When the top cylinder extends, it forces the bottom cylinder to extend at the same rate. When the cylinder reaches its end-of-stroke position, solenoid A replenishing valve should energize to make sure the bottom cylinder is also at its end-of-stroke position.
Yeah, this is in series. Oh, okay, I should put the video. Sorry. So this should come later. Oh, never mind. Okay, we can watch. Okay, okay, so that is what happens when you have a cylinder in parallel. So you have to make sure that both are identical, then you can have both to move at the same time. Unfortunately, I don't have any video for parallel, but you can, in theory, if they are not identical, then the smaller load will move first, okay? Okay, this is parallel. And now we want to see in series. Okay, you have seen the video just now that in series, the movement will be synchronous.
Forces the bottom cylinder.
Yeah, let's just watch again.
Same area where their ports interconnect. When the top cylinder extends, it forces the bottom cylinder to extend at the same rate. When the cylinder reaches its end-of-stroke position, solenoid A replenishing valve should energize to make sure the bottom cylinder is also at its end-of-stroke position. With the top indicator tripped, the replenishing valve shifts, forcing the bottom cylinder to its end of stroke. The same sequence takes place on retract, with the bottom cylinder driving the top cylinder.
Okay, so you can see now during the retraction, when this piston is moving, so you can see that the fluid will lift, the oil will lift from this end and will enter to this end. So that's why when you have two cylinders in series, connected in series, they will move together if you have the same size of the both cylinder having the same size. So you can see here, explanation here. Okay. So this is how it is connected in series. You can see that this end is being connected to this entrance. I mean that the rod end of the cylinder 1 is being channeled to the blank end of cylinder 2. So when cylinder 1 extends, the fluid from its rod end will be delivered to the blank end of cylinder 2. So what happened? The fluid will return to the oil tank from the rod end of cylinder 2 here, go back to the tank, and then return through the DCV back to the tank here. Okay, so in order to have two cylinders to move in synchronous for series connection, the piston area of cylinder 2 must equal. Okay, this is very important. I repeat, maybe I said wrongly just now. In order for the cylinder in series to be synchronous, is not the size of the two cylinder, okay, that have to be equal, because that is actually for in parallel. In parallel, you need to have both equal size and equal diameter and equal length. But in series, it's not the size, but you have to fulfill this requirement, which is the area of the piston 2, this area, piston 2, must equal to the area of piston 1 minus area of rod 1. Okay, because you can see that this connection, this piston 2 is connected to this side, which is AP1 minus AR1. So therefore, these two areas must be equal. AP2 must be equal to AP1 minus AR1. When you achieve this, then you can have the two cylinder to move exactly like this just now. Move together in synchronous. All right. So if you have the connection in series, the pump, this pump, you only have one pump, right? So this pump must be capable of delivering a pressure equal to the pressure required for the piston of cylinder 1 by itself to overcome the loads acting on both cylinder 1 and cylinder 2. Later you can see how can we derive this statement into a formula. So first, let's see. If we do a force summation on cylinder 1, which is this one, cylinder 1, the force summation F1 equal to P1 AP1, okay, P1 AP1 minus P2, okay, P2, which is this one, P2, pressure 2. It's quite blurry here. So this is P1, this is P2, this is P3. Okay, the pressure. Okay, pressure 1, pressure 2, pressure 3. So the summation of cylinder 1, the summation of force equal to P1 AP1 minus P2 times P2 times AP1 minus AR1 equal to F1, this one, the load, okay? And then summation on cylinder 2 is equal to P2 AP2, okay? P2 AP2 minus P3, which is here, and then the area is AP2 minus AR2, okay? AP2 minus AR2 equal to F2. Okay, so these are the force summation each on cylinder 1 and cylinder 2. So when we add these two equations together, and note that AP2, okay, equal to AP1 minus AR1. This area, AP2, is equal to this area, AP1 minus AR1. So when we substitute this, find and also one more thing, that P3 is 0 due to the drain line to the tank. So when we when we substitute both this into the equation, we can get the flow from the force from the pump, which is P1 times AP1, should be equal to the summation of F1 and F2. So this is the mathematical representation to show that the pump is capable of delivering a pressure equal to the pressure required for both cylinder 1 and cylinder 2. Okay, so finally we want to learn about that's about the how can you synchronize the circuit in series. You have to fulfill this requirement, but if it's in parallel, you have to make sure that they are both identical in size so that the load will be the same. Okay. It's not actually the size lah. The most important is actually the loads attached to this. But you know that load is actually pressure equal to F divided by A, right? So the load F equal to P times A. So you have to the key thing here is that you have to have both. Let's say this is F1, this is F2. Okay, so F1 must be equal to F2 in order to have the cylinder to be synchronized. If they are not exactly identical, then you have one will move first, with the lower load, and then after that the one with the higher load will move with the greater pressure increase after the first one has reached the maximum position. Okay. All right. So for cylinder in parallel, the most important thing is the load must be the same. But for series, this area must be the same. AP2 must equal to AP1 minus AR1. Okay, and then lastly, we want to look at the meter in and meter out. So meter in and meter out is, you have to really understand what is the difference, because in your quiz 3, there will be something related to this concept, meter in and meter out. You have to know what is the difference and how can you apply this in order to solve for the question. All right, so meter in means you are controlling the flow into the actuator. So in this case, during the extension only. Okay, how this happen? So means that okay, let me just read this one first. So the term meter in means that you are controlling the flow goes into the cylinder. So that is the basic definition of meter in. Means you throttle the flow or you control the speed of the piston by controlling the flow rate that goes into the cylinder. So in this case, the meter in is only applicable during extension. Okay, and there is no metering, there is no throttle, or there is no control, or there is no flow control done during retraction in this case. I'll show you why from this circuit. So you can see when the cylinder is extending, this check valve is blocked. The flow is blocked through this check valve. So what happened? There is no other option. The flow must go through the throttle valve. This is throttle valve ataupun FCV lah. Okay. If you learn FCV last time, mana ni? Okay. So flow control valve, the most popular one is throttle valve. This symbol, right? Which is this one lah. Okay. But the whole thing here is called one-way flow control valve. It's the one that you use in your experiment, hands-on in the lab, because you have the check valve connected parallel to the flow control valve. Okay. So during extension, what happened? The piston will move in a control speed depending on how do you set the opening of this FCV. However, that was during extension. However, during retraction, which is in the reverse flow, so the flow will go through the rod end and then leaving the blank end. So when the flow is going down to here, with the same orientation of the check valve, this check valve will allow a free flow. So what happened? this check valve will bypass. So this check valve will bypass the throttle valve. So you can just imagine that there is this check valve, this throttle valve is no longer functioning, because the nature of the flow is that they will always choose the path with less or no resistance. So instead of flowing through this flow control valve or throttle valve, it will go through the free flow. That is why during retraction, that's why during the retraction, the piston will move in the 100% of the speed, because nothing is controlled through this one-way flow control valve, because it is set into, because the way how we connect this one-way control valve using the meter in concept. So this is example of meter in during extension only. So I hope that you can relate with your hands-on last time in the lab. You can see the in the pneumatic experiment, okay, you can see that either way, either the extension is being full speed and then retraction is slower, or if you change the one-way flow control valve to the another side, then you can have the other way around. The retraction speed is controlled and the extension speed is full speed. Okay. So this is meter in during extension, and now we want to see meter in. How can we do meter in, but now we want to control the movement during retraction? So what can you do? You change the movement, you place the position of the one-way flow control valve to the connected to the rod end of the cylinder. So now let's simulate. Let's try to do it on the paper here. So you can see that during extension, the flow is going through this way and then leaving. So when the flow is leaving, there will be a free flow. So means that nothing is controlled during extension. Okay, no metering or no flow control during extension because of the free flow here. Okay, so means that it is a 100% speed. This is what happened when you change the position of the one-way FCV. And now during retraction, when you change the CV position here, so during retraction, what happened? This one will be blocked. Okay, this is blocked, and there is no other way that the flow has to go through the throttle valve. And when the flow go through the throttle valve, the flow rate will be controlled depending on how much do you open the valve. So therefore, in this case, the meter in is only during the retraction only. And why do we still call this as meter in? Because we control this retraction when the flow going into the cylinder. Okay, let's go back to the basic definition of meter in. Means we are controlling the flow that goes into the cylinder. For this one, during extension, we control for the flow going into the cylinder. So that's why this is meter in, but only for extension. But this one is also meter in, but during retraction. But why do we call this meter in? Because we are still controlling the flow into the cylinder. The difference is, for this one, the retraction is affected, but for this one, extension is controlled. This one, retraction is controlled, and this one, extension is being controlled. Okay, so that is meter in. And now we want to see what is meter out. Okay. Meter out, the basic definition is when we control the movement of the flow, or when we control the piston movement, or we control the flow rate that goes out from the cylinder. That's why it's meter out. And this is how we can achieve meter out during extension only. I hope you can see the difference. We want to control, since this is meter out, so we want to control the movement when the flow is leaving the actuator. So let's try to simulate. In this case, extension, okay, only extension. So when the DCV is in this position, cylinder will extend, the flow will go in, and then when the oil leaving when the oil leaving the rod end, so what happened here? This is block. So please take a look at the check valve and the seat element. It is very important for you to understand how check valve work. For the check valve, we have seat and then we have ball. So this is a seat, and this one you have like a ball. So whenever you have the flow towards the direction, the ball will be stuck, kan? So when the ball is stuck, there is no flow. But when there is a flow from downward, the ball will be pushed by the pressure a bit upward, and then the flow can move. So that's the basic. I hope it's already clear by with all of you how check valve operate, because then you cannot, if not, you cannot really understand how this one-way flow control valve works. Okay, so when the cylinder is when the flow is leaving the cylinder, this one is blocked, and then what happened during extension? This is being controlled because it has to go through the flow control valve of the throttle valve. So this is meter out during extension only. So now let's prove that during retraction there is no control of the speed. So when there is a movement from the DCV, when the DCV is changed to this position, so the flow will go through this way, and entering the one-way flow control valve, you will have a position of the check valve where it will allow a free flow. So this is a free flow again. So this throttle valve will be bypassed. So when the throttle valve is bypassed, the retraction will undergo 100% of the velocity without any control of the flow rate by this throttle valve, because this throttle valve has been bypassed, means no function at all. Okay, so this is meter out during extension. And again, why do we call this meter out? Because we are controlling this one. We are controlling during extension when the oil is leaving the cylinder. Then we control using the flow. Then we control the flow rate using flow control valve. Okay. So this flow control valve or throttle valve is controlling the flow coming out from the cylinder. That's why we call it as meter out. And how can we achieve the meter out during retraction only? So we move to this, one-way FCV into connected to the blank end. So we want to see that only during retraction. So retract, which is this. Let's look at this lah. Retract. So the CV is in this position. Retract means the flow have to go through the into the rod end and leaving the blank end. When the rod leaving the blank end, again this is block. So this FCV will be active and will control the flow rate depending on how much you set on the opening. So in this case, the retraction is being controlled by using meter out, because you are controlling the flow rate leaving the cylinder to the FCV. Okay, but during extension, you can see there is a free flow. When there is a free flow, this one will be bypassed. The FCV will be bypassed, so cylinder will extend 100% with 100% of the speed. Okay, so I can understand if it's a bit confusing for you between meter in, meter out, but first you have to understand what is the basic definition of meter in and what is the basic definition of meter out. And then if you already understand that, then you can see how do you apply meter in during extension only, and how do you apply meter in during retraction only, and also how you apply meter out during extension only, how you apply meter out during retraction only. It's all about the position of the one-way FCV. Okay, this is one-way FCV, right? The whole thing here. One-way FCV. So it's how you place the one-way FCV in your circuit, and how do you set the orientation of the check valve. If you go back to the first slide, this one, during extension, you can see that the check valve, the ball is facing downward in both sides, extend and retract, right? Also for meter in during retraction only, the ball is facing downward. But for meter out, the ball is facing upward. The ball is upward. Also here, the ball is upward. Okay? But I don't want you to memorize like this, because the most important thing is you understand how the concept of free flow and how is the concept of bypass. If you really understand the concept of free flow and bypass, if I ask you to draw a circuit that implement a meter in or meter out during extension or retraction, then you should know which orientation of the check valve you have to use and in which position to the cylinder that you have to connect, whether to the rod end or whether to the blank end. So this is the video of concept of metering and meter out. I hope it's clearer after you watch this.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Just cylinder, or as fluid is leaving the cylinder. So in this case, we are set up to meter the needle valve. So the way we have this particular flow control plumbed in to the blind end of the cylinder, we are currently set up for a form of flow controlling called meter in. And the word meter in or the word meter out is not a reference to which direction the cylinder is traveling, but rather a reference to whether or not we are controlling the rate of flow as fluid enters the cylinder or as fluid is leaving the cylinder. So in this case, we are set up to meter the fluid as it enters the blind end of the cylinder. Fluid will not be able to pass through the check valve. Here we go. It's all working well in the first part of the cylinder's extension, but as you could see, as the load went over center, things got a little interesting. Now let's watch meter in flow controlling taking place on the line that feeds the rod end port. This will be meter in for the retracting of the cylinder. You could see that fluid is being metered on the bottom line, and oil leaving the blind end port can do so freely through the return flow check valve mounted in parallel to the needle valve. Let's work forward and back again. Now, of course, what's special about this particular...
So you can see this is when you have two units of one-way FCV, one connected to this blank end and one connected to the rod end. So you can see how at the same time it can during retraction, okay, during extension, you will have meter in because this is block. And then during during retraction, you have meter in as well. So you have meter in both during extension and also meter in during retraction. Okay, because when you retract like this, when you retract, this is blocked and the flow will go through the rod end and cylinder will retract. So this is still meter in because you are controlling the flow going into the rod end. And this one is still meter in because you are controlling the flow during extension through the blank end when the oil is going into the cylinder through the blank end. So you can watch this video full, but it's just the same of how did I explain just now. But just now, we never combine both one wave FCV at the same time. We only use one at one time. But in this example, you have both connected. Yeah, like this. This is how can you do meter in flow for both extend and retract. Okay, you can try to simulate this on paper. And this is something that what you have in in your lab sheet. Okay, if you open your lab sheet, you can see for hydraulics lab sheet for hydraulics. Hydraulics pneumatic. This one, right? So you have both connected to the blank end and also to the rod end. But in this experiment, you never adjust the opening here because in this one you are actually testing the pressure relief valve. But actually you have used both. If you try to adjust the setting, you can have meter in for extension and also meter in during retraction. No, in this case, no. In this case, it's different. In this case, during extension, during extension is extension is this way. So it's a free flow. Okay, it's a free flow. Okay, this is actually meter out. Okay, because during extension, the flow goes through here and then this is a free flow. So nothing happened. Free flow through here and the cylinder will extend 100%. Cylinder will extend but not 100% because when the cylinder leaves, this is blocked, right? When this is blocked, this throttle valve will function. So therefore, the throttle valve will control the flow leaving the cylinder. So therefore this is meter out, extend. And then during the retraction, during this through this way, retraction, during retraction, this one is free flow. But when it's leaving, this one is blocked and then this is throttle. So this is also meter out during retraction. Okay, so in this is different from this diagram because in this diagram you can see that the ball is facing downward, but in your lab sheet the ball is facing upward. Okay, so this is meter out for both extension and retraction in your lab, but in this diagram, meter in for both extend and retract. Okay, so you can compare with your lab sheet and also with this. This one is meter in, but in your lab sheet is meter out. Okay, there is a different purpose or different situation. Why do you have to use meter in and when do you have to use meter in and when do you have to use meter out? The first one, when we have to handle resistive load. Resistive load means the direction of the movement of the load is opposite to the direction of the flow. Like this, you see the black arrow is opposite to the blue arrow. So this one we call as resistive load. Therefore, when we have this, we have to use meter in. Resistive load is the load that resists the oil flow. This one. But when you have the so-called tractive load means the flow, the direction of the load, the same with the direction of the flow. Now the flow is going from the blank end to the rod end. So the flow is this direction. So when the direction is the same, we call this as the tractive load. And when you have this, you have to use meter out. Okay. So tractive load is the load that follow the oil flow. So there is an animation, but I think it's the same. Just to show between meter in and meter out.
Here, the flow control valve is placed in the pressure.
I will just skip this because it's just as long as you already understand what is, because I have shown you the video just now, this is already enough to show you the concept of meter in and meter out. So please watch this on your own for the full version, okay? I will provide you the link later for this one. Okay. So lastly, why do we use metering in when extend? Because the load, in this case, the load acts as resistive for this example. And then we use meter out when we retract because the load acts as tractive. Okay, so if you simulate this circuit on the paper, so you can see that during extension, extend means this direction. During extension, the flow is going through this side. This is the direction, but the weight is always acting to the gravity, right? Remember, the weight is always acting downward, gravity. So we have, when during extension, we have resistive load. That's why we have to use meter in. But during retraction, retractions mean, this one lah yang B. The flow is going through this direction. So you have the flow direction downward, and again, the weight direction is also downward. So when you have this same, you have tractive load, and that's why we use meter out. So this is a good example to show why this application use meter in for resistive load or during extension, and why do we use meter out during retraction. It's all because of the type of the load, whether it's resistive or tractive. Okay. Meter in for resistive and meter out for tractive. Okay. So there is a video. I will also provide you the link, like this slide later, so you can watch it on your own. This is a good demonstration on showing you the usage of meter in and meter out together in one circuit. So how can you combine the two concepts, the two principles or the two methods in one application? Okay, so I guess that's all for this topic. So now we have already covered this one. And we have seen all this just now. Okay, so please try to follow this lecture again and again. And if you do have any question, something that you cannot understand, feel free to ask when we meet again on Monday. Okay. All right. So I guess that's all for now. Thank you for your time. And yep, I will see if we have time to. Yeah. On Monday we will have the normal class, and let's see if you have any question from this. please feel free to ask me before we start the next chapter on Monday. Okay. And please bear in mind as well that, yeah, you will next week we'll also do tutorial 4, but that will be on Friday after we completed chapter 7. Okay, so thank you for your time. Sorry for a bit delay in terms of the lecture because I have some interruption on the phone call just now, but also there was some confusion on the slide, but I hope that you can properly follow this lecture. And again, if you have any problem, any question, please feel free to ask when we meet again on Monday. Thank you very much, and Assalamualaikum, and have a good day.